the 3D magnetic field is larger than the plane of the sky magnetic field strength. So in that case, mass to flux ratio will be changed. So we needed to estimate 3D magnetic field strength. So I suggested one method to use both method, thus polarization and GMA measurement. So I already explained the GMA. So if we in those polarization, we can see the line of sky magnetic field strength. GMA can show line of sight magnetic field strength. So we can assume the direction and strengths of 3D magnetic field, the region. And there are a few previous studies try this. The long time ago, there is optical polarization H1 GMA have been used to estimate 3D magnetic field orientation strengths. But the problem is H1 press diffuse region, not performing region actually. So in this region, we can use CN GMA measurement. So we can trace the 10 to 5 number density. So by using those polarization and CN GMA measurements, we can estimate 3D magnetic field strength in high mass forming regions. But the problem is the CN and dust emission have to trace the similar density regions. If not, it is trace another area. So we needed to check the first their correlation between CN and dust emissions. So I suggested the observation toward the TRA. The TRA is a 40-meter radio telescope located in Daejeon, but unfortunately it is shut down the last year, so we cannot use it anymore. Anyway, I did a CN motif map toward the 6 high mass forming region and compared with the dust emission obtained by the Herschel. So this is the CN lines. So it has the 7 hyperfine lines, and among the hyperfine lines, we chose the most optically thin lines to compare the dust emission. That is this hyperfine component. And then this is the integrated intensity map of the CN, and this is the dust emission map. So to compare both emission, we calculated the column density of CN and dust from the emissions. And then we estimated the correlation coefficient between the CN column density and H column density. And then we can find that it is quite good correlation coefficient, except the residual H and ER given, but others rather than 0.7. And we also checked the peak position of the CN column density and dust column density, and it is well matched within the 1B of the beam size TRL. And based on that, they show good correlation. We can estimate the magnetic field strengths using the CN GMA measurement and dust polarization. So I collected the JCMP polarization observations and CN GMA measurements and estimated the bound 3D magnetic field. As to as you explained it before, the line BCF method can overestimate more than factor of 4 larger magnetic field strength compared to the GMA. So we applied that statistical value to correct this value. Then we can show that most of the high mass forming region, as we expected, is magnetically supercritical. So, but we needed to more study to estimate the 3D magnetic field strengths using ALMA or MeerKAT. And we need more GMA observations, so I'm doing KBN, ALMA, whereas MeerKAT, the GMA measurement project is. So keep in touch about that. So that's all. Thank you.
Thank you very much. So any questions from audience? Yes.
So thank you. So you mentioned that in the future plan you plan to use ALMA and Meerkat. So what data from Meerkat are you going to use? Synchrotron polarization or Zeeman data?
So in case of ALMA, we can do simultaneously dust polarity.
Yeah. But in Meerkat, I'm talking about Meerkat.
In case of Meerkat, also there is the continuum data and OH major or OH line.
I see. But how about the potential uses of SKA?
Yeah, SK, Meerkat will be the SK later. So
Okay.
yeah, we can use the SK.
Yeah.
also.
Okay, good. Yeah, I think
Yeah,
it's very interesting. Yeah.
Yeah, but now we cannot use SK. So I just.
So this is a near future, not. Okay, thank you.
Yes.
Thanks for a very nice talk. And could you elaborate a little bit more on the advantages of your method and the moving box method, and how is it compared to other methods such as the structure function method? And I am also would like to understand more how did you calculate the volume density, the depth for each regions.
Yeah. So first question is compared to the structure functions. So in case of a structure function, also if we can use the just turbulent scale, in case of a structure function, we assume the turbulent components and ordered component. So it is increase the distance from the pixel. It is ordered component is dominated, and the turbulent part is the just 3 beams within or 2 beam. So if just use the within 2 beam, the structure function and moving boxes same condition. So we can see the distribution of magnetic stresses. So it is suggested by COS in using the SOPHIA data. So anyway, that method, my method strength is we can see the distribution of magnetic stresses. So that's the difference previous studies. The previous study just one mean values toward the large OMC1 region. So, and the second point, volume density. In that case, the filamentary structure, I did find the filamentary measurements using field finder algorithm, and then find the width of the filament, and then divided the width toward the column density. So it is actually we can slightly large volume density compared to the assumed cylindrical structures. So it could be slightly underestimated the volume density.
Such as the case of G28, it looks rather complex. So you still use the filamentary G28?
G28 is I used the Austro-Dendron algorithm and find the clump structures and assume the spherical structures and divided by rod. But anyway, if we assume the spherical structure, the depth will be changed as the radius.
Life size.
Yeah. But it is weird. So the outer part is much high density. So I just divided the same widths. But anyway, there is uncertainty.
Okay. So probably you guys question by Jiawei.
Hello. So I would like to comment on the uncertainty of DCF, but because of the density. So as you mentioned, on the parsecs scale, most clouds are filamentary, not spherical. So also we can measure the width on the plane of sky. So let's say it's W, but because of the inclination, so the actual thickness of the filament is the W divided by cosine theta. So you can imagine when the inclination angle is high, the cosine theta becomes close to 0, then the actual is much higher than we expect. And also the other issue is if we assume a constant thickness, then we will tend to underestimate the thickness on the outskirt, and we will because they are more diffuse, and we will overestimate the thickness in the dense structure, dense regions. So when we are trying to analyze the correlation between the magnetic field strength and the density, we will have a strong bias because of this thickness. Yeah, so that's all the problem for DCF method, and I also don't have good solution.
That's true. We have to include the inclination effect. It is affected not only the magnetic field, just it is affected by the column density and number density also, the inclination angle. So yeah, that's true, but it is hard to assume that one. So I just assumed on the plane of the sky.
Okay, great. So let's continue our discussion in the discussion session. So let's thank our speaker again. Thanks. So our next talk will be given by Bao. Yeah, so he will talk about to probe 3D magnetic field structure using grain alignment and dust polarization. So you can start whenever you are ready. I will let you know when it's 5 minutes now.
Okay, so good morning, good afternoon, good evening, wherever you are. So I'm Bao Trung, and currently I'm a PhD student at Kazhi University. So it is my pleasure to be here and giving a talk about the in the 3D magnetic field section. So today I would like to introduce a new technique to trace the 3D magnetic field using dust polarization combined with the grain alignment theory that we heard previously from Professor Tim Huang talk. And so today I would like to go through about how we develop the new technique and how we apply the new technique to the real observational data. Okay, so far we can see that the way that we study about 3D magnetic field is really important to understand about their role in star formation processes. So from the large scale, like in molecular cloud scale, the study of 3D magnetic field is really important to predict the cloud formation scenario, as well as we can use the 3D magnetic field to understand about their impact onto the evolution of the filament. And toward to the smaller scale, we can use the 3D magnetic field to justify about our class shape model. And if we have the 3D magnetic field information, we can compare in terms of the energy balance between 3D magnetic field, turbulence, and gravity, so that we can understand further about their role in star formation processes. Besides, understanding about 3D magnetic field is really important to understand about cosmic ray transport from the outer to the inner region in the Milky Way. So there are certain attempts to trace 3D magnetic field using the observational data. So we heard that from Tahani talk that we can use both the line of sight magnetic field that we can get from the Faraday rotation, combine that with the plane of sky magnetic field that we can get from thermal dust polarization to get the 3D information. And we can see that from the Yue talk that we can use the velocity gradient technique for different gas tracer, combined with the convolution neural network in order to get the 3D magnetic field information. So in this talk, I would like to emphasize that by only using the dust polarization degree, we can also trace the inclination angle of the magnetic field. So this is the angle between the magnetic field and the line of sight, and combine that with the 2D information of magnetic field in the plane of sky, so we can have the general picture about the 3D magnetic field structure and how they impact onto the star formation processes. And and to use the dust polarization degree to trace the 3D magnetic field, so several factors that need to be taken into account. So the effect of, so the dust polarization degree not only just affected by the inclination angle, but also affected by the tangling of the magnetic field that is causing due to the turbulence as well. And besides, for the dust variation degree, it strongly affects about the way that grain can be aligned with the magnetic field by relative torque, as we heard previously from Professor Tim Huang talk. And this alignment also depends both the environmental condition like the radiation and gas property, as well as the dust property itself. So the effect of realignment should be taken into account in order to use the dust variation degree to trace the 3D magnetic field. So a detailed physical model of dust variation degree should be developed and take all of these factors into account to truly understand how we can use the dust variation degree to get the inclination angle. So this brings us to the motivation about how we develop a new technique. So in here, we develop a new technique to trace the 3D magnetic field using dust variation degree combined with the realignment theory. And this new technique not only just used for the polarization from starlight absorption that we see that in the optical and near-infrared wavelength, but also we can use that to the polarization from the thermal dust emission that we can observe from far-infrared and sub-millimeter wavelength. So firstly, we developed the new technique to trace the 3D magnetic field using the polarization of thermal dust emission. In order to do that, we developed the physical model of thermal dust variation degree as shown here in this formula. And this depends on four main factors. So firstly, is the PI. So this is the polarization from the intrinsic dust property. And this is depend on the grain shape and also the size distribution of the grain in the local environment. Secondly is the FLI. So this is tell us about how the grain can be efficiently aligned with the magnetic field, and this is depend on both the environmental condition, such as the radiation and gas property, and also the grain magnetic properties for the parametric grain and subparametric grain with the iron inclusion itself. And the third one is the factor that is caused by the magnetic turbulence that we can characterize from the fluctuation of the magnetic field between the local one and the mean magnetic field. And finally, of course, is the inclination of the mean field with respect to the line of sight. So if we have the polarization degree that we can get from observation, and if we can characterize the first three main factors, the PI, the FLI, and the F turbulence, so we can use that in order to determine the inclination angle of the mean field in local environment. And this new technique not only just apply for the diffuse medium and also in the large scale in molecular cloud, but also it can be applied to trace the 3D magnetic field in toward to the smaller scale with denser intensity, with high density, such as the filament and also the dense core. So we first test the new technique to the synthetic data. So here we use the MHD data for the filamentary cloud undergo the self-gravity by Hennenberg and Tomosi in 2019. And from the environmental properties of the filamentary cloud, such as the gas density, and also the radiation field. So we can use that in order to calculate how the grain can be efficiently aligned with the magnetic field that I show in here in the F alignment. So from the MHD data, so we use the Polaris course that we can generate the synthetic dust polarization. So for the brief introduction, so Polaris course is the 3D relative transfer code that can generate the synthetic dust polarization based on the modern realignment theory. And recently, PhD student Zhang Wing, she also include the MRAD alignment, so that the code not only just apply to generate for different grain magnetic properties, but also for various scale from the large scale to the smaller scale, just as the protostar core. So we can hear more about the code in the tomorrow talk by Zhang. And for the F turbulence, so we can characterize from the MHD data from the fluctuation between the magnetic field and also between the local magnetic field and the mean field. And if we have other ingredients together, so we can use that in order to calculate the inclination angle of the magnetic field from pixel to pixel in the molecular filamentary cloud. So this is shows about the result, this is showed about the result when we get about the inclination angle from the dust polarization degree when we include the grain alignment that I show in here in the solid color solid line. And we also compare that with a reverse technique that is developed by Chen, also use the polarization degree to trace the 3D magnetic field. But in this case, they assume that the grain alignment is uniform. So it is shown here in the color dashed line. And we also compare in terms of inclination angle that we get from two techniques with the inclination angle that we can get from the MHD data that I show in here in the black line. So one, we can see that when we consider the grain alignment, So our new technique will prove the inclination angle of the magnetic field more closer to the true mean angle of the magnetic field that we can get from the MHD data. And on the right here, it shows the deviation between the angle that we infer from our technique and also the angle that we can get from the MHD data. So we can see that our technique provides a less deviation to the MHD data by the deviation about 2 to 5 degrees. So we also extend the new technique to trace the 3D electric field using the polarization from starlight absorption. And to do that, we also developed the physical model of the starlight polarization efficiency. And also it depends on 4 main factors at the same as that we did in the thermal dust polarization. However, for the case of a starlight polarization, it's sensitive to the observed wavelength and also the grain size. So instead of using the FLI as I introduced earlier, so we're using the F-pole. So this is the fraction of linear polarization coefficient of a light grain over to the total of the polarization coefficient of the whole grain size distribution. And this is depend on the wavelength size distribution and also the grain alignment degree for the certain grain size. So if we have the starlight polarization efficiency, the polarization degree over the column density or over the visual extinction, and if we can characterize the first three parameters, the PI, this F-pole, and also the F turbulent, so we can use that in order to determine the inclination angle of the magnetic field at the same as that we did in the case of the thermal dust polarization. So, okay. So this is the result when we try to test that with the synthetic starlight polarization data. We also use the Polaris code to generate data and also to apply the new technique to trace the inclination angle. So on the top in here is in the way that we use that in the optical wavelength, and on the bottom in here is when we use it in the near-infrared wavelength. So the possibility of trace 3D magnetic field is depend on the observed wavelength. So when we're using the optical polarization, so mostly we trace the 3D magnetic inclination angle mostly in the environment that is less density with the visual extinction could be less than 3. But if we use the near-infrared polarization, so we can trace further to the higher density region, and the visual extinction can be go up to about like 30 in this case. And despite the difference in terms of the observed wavelength, so our new technique, when we're including the grain alignment, so we can provide the accurate inference of the inclination angle, which is closer to the true mean angle of the magnetic field that we get from MHD data with the deviation about 2 to 5 degrees. And also our latest paper, when we're using a starlight polarization, it also presents that in the AAA journal Outer series. And if you want to have further information, more detail, so you can go to the YouTube, and then it's informal but engaging way to understand further about how we develop the new technique. So that is the way that we develop the new technique, and also we test that to the synthetic data. So how about we apply to the real observational data? So to apply the real observational data, so the intrinsic dust property, the grain alignment by the Ambra theory, and also the magnetic turbulence should be first characterized in order to use the observed dust variation. And from that, we can use that to calculate the inclination angle of the mean field with respect to the line of sight. So for each factor, so from observation, for instance, for the intrinsic dust properties like the size distribution and also the grain shape, we can constrain that from the maximum polarization degree, and also we combine that with other tracers, such as the dust extinction curve that we can get from optical and near-infrared wavelength, or the spectral index that we can get from the SED fitting at 500 submillimeter to get the intrinsic dust polarization. From the grain alignment properties, so we can constrain from the local environment conditions, such as the gas number density, the gas temperature, dust temperature, and even for the magnetic field strength. And from that, we can use the Ambra theory in order to calculate how the grain can be efficiently aligned with the magnetic field. For the magnetic turbulence, so we can use the dispersion of the polarization angle in the plane of sky in order to derive about the magnetic turbulence factor. And if we have all our ingredients together and combine that with the observed dust polarization, maybe it's the dust polarization degree in the thermal dust polarization or the starlight polarization efficiency. So now we can use that in order to trace the 3D inclination angle. So we first apply the new technique to the case of the G11 filament. So G11 filament is the massive filament in the early phase of massive star formation. So for the G11 filament, it have both the starlight and also thermal dust polarization data. So for the starlight polarization data, it is observed by Serpo at K-band by Z-wave chain in 2023. And for the case of thermal dust polarization, it's observed by Sophia Hopeless and analyzed by another PhD student, Ngọc Nguyễn, in 2023 as well. And for the case of starlight polarization, it's mostly traced the magnetic field in the outer envelope of the G11 filament. Why? When we're using the thermal dust polarization from Sophia, so we can trace mostly to the denser environment, to the denser filament. So when we apply the new technique to both the starlight and also thermal dust polarization, so we can use that in order to prove the 3D magnetic field in multiple scale from the outer envelope of the G11 to the smaller scale in the denser inner region of the G11 filament. And in here, I would like to show how we apply the new technique to the case of the starlight polarization. So which means that we can prove the 3D magnetic field in the outer envelope of the G11. So firstly, we need to constrain about the intrinsic dust property, and from that we can get the intrinsic dust polarization. So in order to do that, so we use the interstellar dust extinction that we can get from Gaia, and also we analyze, so it's being analyzed by Zhang et al. In 2025. And from the dust extinction curve, so we can use the shape of the extinction curve that we derive the RV in here. And from the shape of the extinction, so if the RV in here, the total to selected ratio is increasing, so it means that the shape of extinction curve is more flatter, and which means that the grain size is more higher. So which means that from the shape of extinction curve, so we can use that in order to constrain the maximum grain size as well. So from the maximum grain size that we constrained earlier from the interstellar dust extinction, so we can combine that with the maximum polarization efficiency that we measure, that is previously measured by Z-wave chain. And from that, we compare the maximum polarization efficiency with the model maximum polarization efficiency that we can use the dot profile to generate based on the Embrad alignment theory that we see that introduced by Trọng Talk yesterday. And here, when we consider about maximum polarization efficiency, we consider that at the maximum point, the grain alignment is efficiently aligned with the magnetic field, and the magnetic field in here is mostly aligned to the plane of sky and also well ordered. So we mean that in the maximum, it attributes to the intrinsic dust polarization burst properties, and combine that with the maximum grain size that we constrained previously, so we can use that in a constraint about the shape of the grain or the grain ratio. And finally, based on the observations, so we constrain that the maximum grain size is about like 0.25 micrometer. It's the same in the interstellar medium, and also the grain ratio is about 1.6 in order to explain about the observation from both data. So step two, after we have the intrinsic dust properties, so we can use the environmental condition and the constraint about the dragline efficiency. So here we use the modified Black-Body fitting from the multi-wavelength Herschel observation in order to derive about the gas number density and also the temperature, and combine that with the intrinsic dust properties. So finally, we can use that in order to calculate how the grain can be efficiently aligned with the magnetic field in the case of the G11 filament. So after that, we also need to characterize how the turbulence can affect to the observation of the polarization. So here from the starlight polarization data, so we split the data into many grid cells, and each grid cell is about have the size about 2 by 2 arc-minute, and we calculate the dispersion inside that cell, and from the dispersion, so we can use that in order to calculate about the magnetic turbulence factor. And so now we on our information that we can get from observational data, so we get the intrinsic dust property and also the grain alignment that we can constrain from the Embrad alignment theory, and also the magnetic turbulence that we can get from the dispersion of the polarization angle, and combine that with the observed starlight polarization efficiency, so we can use that in order to calculate the 3D inclination angle of the magnetic field. So if we have the information about the inclination angle of the magnetic field, so we can use that in order to calculate the 3D magnetic field strength. So here I'm using the 2D magnetic field strength that we can calculate from the DCF method, and then we divide it with the sine of the inclination angle that we found earlier, so we can get that the 3D magnetic field strength. And one, you can see that compared to the 2D value, the 3D magnetic field strength is higher. So from the 3D magnetic field strength, so I use that to calculate the energy balance between the magnetic field and also with turbulence that is described by the average Mach number, and also the magnetic field and gravity that is described by the mass to bulk ratio. And since the 3D magnetic field strength is much higher, so compared to the 2D value, so we can see that It's a reason about lower average Mach number and also lower the mass to work ratio. And this drives to the conclusion that for this filament, the effect of the 3D magnetic field is dominated, which is sub-average and also subcritical, and go to the denser environment, it's become more transcritical. And from the information about the inclination angle, so we can combine that with the 2D polarization angle that we can get from the observational data in order to get the 3D morphology about in the case of the filament. So here we are like for three reasons, A, B, C. So this is the three reasons where it's the magnetic field it shows to be perpendicular to the filament structure, and on the right here it shows the variation of the inclination angle from the outer to the inner region of the filament. So it's different based on the each region. So for region A, so you can see that by analyze about the inclination angle, we can see that mostly the magnetic field in here is uniform, and also inclined with respect to the line of sight is about like 60 degrees. But toward to the region B, so here we can see that the inclination angle tend to be increased when we go to the denser, tend to be increased, which means it's lying to plane of sky when it going to the denser environment, into denser filament. So this is show us that the magnetic field in here, it tends to be bended with respect to the line of sight. And for the reason C, so this is the reason where the self-gravity is quite completely strong and they have the massive plumb formation. So since the effect of the self-gravity, so it can twist the magnetic field, and that is causing the magnetic field to be more inclined with respect to the line of sight. And that's why when we analyze toward to the inner region, to the inner dense region, so we can see that the inclination angle tend to be decreased for the case of region C. So this from the inclination angle and combined with the 2D information, so we can have the 3D information, 3D structure of the magnetic field in overview. So this is how we apply the new technique to the real observational data. And in order to do that, we need to constrain both the intrinsic dust property, the error alignment, and also the magnetic turbulence. And the intrinsic dust property, both the size distribution and also the grain shape, is the most important factor. However, it's also affect with respect to the different local environment due to the grain evolution, so that the grain growth and also the grain disruption, and it will cause the degeneracy when we try to accurately trace the 3D magnetic field using the dust variation degree. So how we can do that at the same time, both the 3D magnetic field and the dust property? So it is time for us to thinking about using the deep learning model to do that at the same time. So the key idea is that if we have the observational data for both, maybe for the thermal dust variation or the starlight variation, so we can use the deep learning model, such as the neural network, CNN, and vision transformer. And finally, we can get the related output, both the 3D magnetic field and also the dust property. And this one can be generated at the same time. So this project is currently under development, so stay tuned for the new coming result. So since I know that I have run out of time, so this means thank you so much for your listening, and I'm glad to have a question from the audience.
Thank you, Bao. Any questions? Yes.
Okay, hi, Bao. Great talk. So I have maybe two comments. The first comment is that when you calculate the F-turb, the turbulence factor, and your simplified equation used for the subaphanic cloud. So you need to be say clear, because in your simulation you can calculate that, but when we apply to observation from the polarization angle, right? It's just apply for the subaphanic cloud. So you need to see where we can apply it. That's the first comment. The second comment question basically is that when you said that we use the technique to apply, I just discussed with him, to apply to the starlight polarization, and you show the application to the optical and near infrared. And how about in the future we have the UV polarimetry, which RAD cannot be responsible for the alignment. Could you improve your model to work on the UV polarimetry using DG alignment theory rather than AND-RAD theory?
Okay, you mean we need to improve more to the DG alignment?
Yeah, how do you think you can just replace the RAD theory by the DG theory and apply the same thing for the 3D magnetic field with the future UV polarimetry?
Yeah, I think that's I think that's case. Okay, I will. Firstly, I wanted to answer about your first comment. So yeah, that's right. So when we apply to the synthetic data, so here for the cloud, it's mostly sub-avalanche. And the reason, the also main reason for the choosing for the when you apply to the KFG11, and also from the plane of sky observation, it shows that move starlight and also thermal dust variation is also sub-avalanche. So that's why the reason, and this is also the ideal candidate to test the new technique to this to this kind of cloud. Is the first comment. The second comment is that yes, if we improve about the DG alignment into the alignment function, and then we can put that into the dust profile, and then we can use the UV polarimetry in order to trace the 3D magnetic field. However, for the case of UV polarimetry, so because that optically thick, so which means mostly it only can trace in the diffuse medium as yeah, it's much more larger area compared to the case in the filament.
Okay, so we have question for online participants. So Manush, please.
Yeah, Manush.
Can you hear us?
I think that she have not yet turned.
Hi, yes, yeah. I didn't have permission to unmute. Yes, thank you for the nice talk. So I'm wondering how you address the line of sight confusion, the direction, and also the plane of the sky direction. In a review paper that I wrote in 2022, that you've also cited as well, figure 2 of the paper shows two morphologies where we even know the line of sight direction, but we don't know the plane of the sky direction, and we end up getting two possible perpendicular magnetic fields that could explain if we have the inclination angle and the plane of sky orientation. So I'm wondering how you address the lack of plane of sky direction and the lack of line of sight direction. Thank you.
Okay, so thank you. Okay, thank you, Manoj, for your question. So here from our new technique, we can guess the 3D inclination angle that we can get from the dust tree, and from the dust polarization, we know about the 2D direction of the polarization. However, from the dust polarization, we only can get the absolute value of the inclination angle. So we cannot get the direction, the proper direction about the line of sight is pointing toward us, or is it backward to us during observation. So I'm thinking like from your technique, when you're using the Faraday equation, you also have the direction in the line of sight direction, and combine that with the inclination angle that we can get from our new technique, so we can see that how the magnetic field actually have been curved with respect to the line of sight in terms of the geometry and also in terms of the direction, 3D direction as well. So that is about my comment in this.
Okay, so one more question for online participants. Shahana, please.
Okay, thank you for the nice talk. So my question is that you in 17th slide you showed the means value of B in 3D and B plane of sight from this. So means what is the factor which is coming means what is the difference between B 3D and B plane of sky, sorry. So what is the factor? For example, in general, but we use that B means total B is equal to 1.3 into B plane of sky. So here, how much factor you are getting, and what are the environments in which B plane of sky and B total B 3D will be similar, and what are the environments in which there will be a larger difference? Yeah, thank you. Did you get it?
Yeah, it's repeat your 17, okay. Oh, this one?
Yeah. So the difference. Okay, so.
Yeah. Well, for the strength.
Okay, so Yeah, so okay, so I was asking that what are the environments in which the difference between these two columns will be smaller, and what are the environments in which the difference can be larger? Means in which cases we need to apply, we definitely should apply B3D for any further investigation.
Oh yeah. Oh, for the case of G11, in this case, or apply for the for each pixel by pixel. So we have the spatial angle from the star operation by pixel. So as you can see that in the right panel. So I calculate the inclination angle from that, and based from that, I calculate the plane of sky using the DCF method, and then divide it with the inclination angle that we found, so that we can get the. Yeah. So this is the value that this is the way we calculate for pixel. So for region A, B, C that I summarize here is just the average value that we can get from each region.
Yeah.
Okay, so any last questions? Okay, if now we can continue in the discussion session. Yeah. Okay, so let's move on to the last talk for this morning. And Shivani, are you ready?
Yes, sir.
Okay, you can start whenever you are ready.
1 second.
Yeah, so it's a 15 minutes presentation. So I'll remind you when you have 2 minutes left. Yeah.
Is my slides visible?
Yeah, please start.
Okay. Okay. Hi everyone, my name is Shivani Gupta, and today I will discuss about one of my research work, magnetic field on different spatial scales of L328 cloud, and this work is done under the supervision of Dr. Archana Som. So the motivation behind this work is how do magnetic field morphology and strength differ on different spatial scales, and how their polarization and intensity varies. And we also talk about why some chemically evolved cores do not form stars. So first we will talk about L328 cloud. So here we can see L328 cloud, which is located at a distance of 217 parsec and having head-to-tail morphology. And when we zoom in this rectangular box with the help of NIR, we can see there is a dark patch which contains L328 core. When we again zoom in this rectangular box with the help of sub-millimeter emission by using JCMT, we can see that L328 core having 3 subcores S1, S2, and S3. But there is something special about S2 subcore. S2 subcore contains a very low luminosity objects. They basically share the same characteristics with typical protostars, but they are having low bolometric temperature, very low luminosity, and weaker outflows compared to class 0 and 1 low mass stars. Because of all these 3 properties, they will have minimum turbulence effect on the surroundings, and because of this, it may preserve the primordial magnetic field in this region. So to analyze magnetic field morphology, first I will tell about all the that in all the figures this star symbol represents the S2 subcore, and that contains Velo, and these double-headed arrows shows the bipolar direction of bipolar jets. And in the first figure we can see that the magnetic field is mapped by the Planck, which traces large scale magnetic field. Here we can see that in this region, the overall orientation is northeast southwest direction, and B field is also parallel to the cloud's major axis, which also shows the frozen in effect. But when we trace the same molecular cloud with the help of optical band, we can see that the magnetic field is excuse me. I put it on. The magnetic field is randomized in nature. It may be because it is possibly influenced by external factor, but despite of overall randomness, it maintains our overall trend of maintaining northeast southwest directions. When we again zoom in this rectangular box, we can see that that it is tracing envelope scale magnetic field by using these three color coded vectors, which represents J, H, and K band. At given RA and DEC, we can see that it is showing same morphology, which also indicates that magnetic fields are structured at NIR scales. When we try to see the magnetic field morphology at core scales, we can see that the field lines are appear to wrap around the outer boundary of the core, and also when we see in the figure C and D, we can say that the magnetic field morphology at the envelope scale and the magnetic field morphology at the core scale is approximately similar. So we can say that there is a clear connection between the envelope scale morphology and core scale morphology. To summarize this, we can say that cloud scale B field is well connected to the core scale B fields by showing an overall orientation in northeast southwest direction. This also indicates that core is embedded in strong magnetic field. To investigate that, we will find the magnetic field strength by using modified Davis-Chandrasekhar Fermi method. First, we will calculate the volume density by estimating the mass of the L328 core. And to calculate mass, we first find out the temperature of L328 core. That's come out to be 11 Kelvin, and the mass of the L328 core comes out to be 0.69 solar mass. From here, we estimated the volume density, and to find out the FWHM of gas velocity, we use the spectroscopic data. By using N2H plus line, we determine FWHM of the gas velocities, and by using polarization data, we find the dispersion in angle. By using all these three values, we find that the scale magnetic field comes out to be around 50 microgauss. At the envelope scale, the magnetic field is 22 microgauss. This indicates that core scale magnetic field strength is approximately 2.5 times larger than the envelope scales. That suggests that higher magnetic field strength in the core, possibly due to core collapse or enhanced magnetic flux. As we already found the magnetic field strength, we can compare the energy budget of L328 core by comparing their gravitational energy, thermal kinetic energy, non-thermal kinetic energy, and magnetic energies. Here we can see that the thermal kinetic energy is less than by a factor of 10, which suggests there is a tendency for the core to collapse, but the presence of significant magnetic and turbulence energies indicate that these forces may counter the gravitational pull, potentially delaying or regulating the core collapse process within the core. Further, we will investigate mass to flux ratio in L328 core. Mass to flux ratio represents the balance between magnetic support and gravitational collapse, and it is represented by this equation. If lambda is less than 1, we can say that the core is magnetically subcritical, which means magnetic field will provide support against gravitational collapse. If lambda is greater than 1, we will say the core is magnetically supercritical. It means magnetic field will be insufficient to prevent gravitational collapse. Hence, it will lead to star formation. For the L328 core, we found that lambda is around 1, which suggests that core is transcritical. Further, we compare these mass to flux ratios for the core L1521F and L328. We see that they are having IRS sources, but they are less chemically evolved. Uh, so the reason behind this may be their supercriticality, which suggests that an imminent collapse. But for the other 3 cores, we can see these cores are chemically evolved, but they are still starless. It may be because of their subcriticality. Because of that, these cores are still starless, but we can't say anything conclusive. We need more studies on this. Finally, we analyze polarization and intensity variations in the L328 core. Here in this figure, we can clearly see the hints of polarization hole, and to analyze this, we have plotted polarization versus intensity plot. Here we can find a negative correlation with the slope of 0.98, and the possible causes for this depolarization effect may be because in denser regions there is a change in the magnetic field orientation, or it may be because of magnetic tangling, and inside the cores there can be a weakening of red due to insufficient radiation, and in the denser region gas grain collisions also become effective, and it leads to reduce in the strain alignment. So this is the summary of my talk, and thank you. I hope.
Okay, thank you very much, Shivani. So any questions from audience, in person or online? Yeah. Yeah, any questions? Yeah, I have one. So when you show the energy ratio between
Yes, sir.
the gravity turbulence, right? So what's the typical uncertainty of these numbers?
So these are having typically uncertainties of approximately 10%, means
10%.
0.1. Yeah.
Oh, okay, pretty good. Yeah. So we have one question from Shahana. So please go
Yes.
ahead.
Yeah. Shivani, I just missed that. How you calculated temperature? Where you showed that for mass? Yeah, this one.
For this, I used uh, uh, flux density at different wavelengths, and I fit it with the modified black body.
Okay, so you and from where you took the flux density for different wavelength?
For some, I use Herschel data, and for 1200, I use ALMA data, and 850 from JCMT, and 350 was from one archive.
Okay, so the previously shown. Okay, yeah, thank you.
Okay, so if there's no further questions, let's thank our speaker again. And that's all the talk we have for this morning. And then we'll move on to a discussion session. And then
Hello, so I'm asked to lead the discussion in this section. And since this section is about the method to measure the 3D magnetic field, so here I just summarize some of the topics that we can discuss. And I organize these topics in 4 levels. So the first level is, since we have several techniques, so when we are trying to apply a technique to a specific research topic, then we need to know what's the limitation, what's the requirement of each techniques. And if it's okay, then we can try to use different techniques. And if we have results from different techniques, then we need to know what we need to consider when we are trying to compare the result from different techniques. And if the results are comparable, then the next step is we can try to cross validation the reliability of different techniques. And in the final step, we can think about how shall we analyze the 3D magnetic fields. So go next. How to go next page? Okay, so for the first topic, because we have different techniques and all the techniques have some basic assumption and limitation. For example, for the Faraday rotation, we want to measure the rotation of the background sources. So first we need to have appropriate background sources, and this will also limit our availability to probe the region that we might always have the appropriate background sources. And it has some limitation in the high density region where there might be high electron density that will cause the Faraday rotation to cancel each out. And for Zeeman measurement, because we can only measure the Zeeman splitting in certain tracers, and currently we only have very limited choice. And the other issue is that in order to order Zeeman, we need to really know what's the chemical structure, and we have an extremely high signal to noise. So usually we can only measure Zeeman in very bright region and with very low resolution. And for dust alignment, I leave it blank because I think many people here can explain it better to me. So please comment this later. And we can also talk about the spectroscopy method. And this is also based on the NHD simulations, similar to the VHT method. And so they will have similar limitation that because this method is based on the balance between the magnetic and turbulent energy. So when we are moving to the high density region, where the stable state of gravity becomes important, and we have some other non-turbulent kinematic energy, the balance between the turbulence and the magnetic field could be break. So that's why in yesterday Archana's talk shows the VGT method can sometimes be failed in high density regions. And when we are trying to compare different methods, what we need to consider is are they tracing the same regions? And because we are tracing very different environment using different tracer for each method, so it's actually a very complex issue that we need to be aware. And the other issue is that we really want to know what are the scale we are probing. So for dust emission, it's maybe more simpler, but for Faraday rotation and starlight polarization, because we are looking at the point source, so the resolution is actually very, very high. So how shall we quantify what are the scale we are really probing if we are looking at a point source? And that is also a very difficult question when we are comparing the starlight polarization and the Faraday rotation to other methods. And the third issue is, since we have a new method, same method multiplied by the grain alignment, then we will need to really test the method from observation. So what do we need? So maybe we can try to use the Zeeman measurements compared with the result from the dust alignment technique, and if we have multiple, if we are trying to validate the result from multiple techniques, then what can we learn? Maybe we can try to constrain more on dust property. Maybe we can constrain more chemical model. And the other question is, for as an observer, we usually only measure one observation, like say we are measuring the polarization, dust emission polarization. But in order to better constrain the dust model, then what observations we need? And the fourth topic is, how should we analyze the 3D magnetic fields? And we are keep saying 3D, but it's actually a confusing term, because here the 3D means we measure the line of sight component. But for theorists, 3D means the magnetic field in a 3D cube. And that is very different from what we are saying here. So we mentioned this topic a few times in some talks, but I think we might still have better discussion on how to really know the magnetic field distribution in a 3D cube. And we also discussed about the magnetic field strength. We know DCF method has many problems, and the Zeeman is probably the most reliable way. But Zeeman only provide the magnetic field strength in the line of sight. And then in this case, we still don't know the plane of sky component. Then maybe we can try to use the dust alignment model to revalidate the DCF method to get the total magnetic field strength. So here is the topics we can discuss. So any comments from the audience? Okay, please. Okay.
So, hello. Hello. So thank you very much for the details. So I have comments for maybe the what we need from observational point of view to have more information. So I think as Bao showed that he would like to know the maximum grain size, right? Yeah, I think. Yeah, I think the information we can have from observation, the extinction curve, also the total SCD, somehow we can help to.
So what kind of observation we need to know those properties?
Yeah, I think on top of the multiple wavelength dust polarimetry, degree polarization, if we have the extinction curve or the dust SCD, it could help us to have the better constraint on the maximum of grain size.
Yeah,
I think one more can help to reduce the decision accuracy.
Yeah, so I would like to elaborate a little bit more. So the technique to derive 3D magnetic fields using dust polarization and grain alignment, we really need the dust properties.
Yeah.
So in terms of observation, the dust properties we can constrain is the grain size and also grain shape.
Yeah.
So for, of course, the grain size can be constrained by extinction curves, but extinction curves now we can use the data not only from optical to near infrared, but we can also use the extinction in mid infrared traced by JWST.
Okay,
So,
but
for dense region, grains grow can be very efficient. So only mid infrared extinction can allow us to constrain the micron size in protostellar environments.
yeah, but for in dense star forming region, we usually can only observe in sublimeter. So
But the more popular technique to constrain grain sizes is using the SCD in sublimeter multi-wavelength. So with the JCMT, ALMA, and Herschel for larger scales, but for protocell core scales, we can have ALMA. So there's a very big community who are interested in understanding dust properties. So I think for applying our new technique, we can take advantage of the existing SCD observation. But what we want to constrain here is a grain elongation. And the grain elongation can be only constrained using the polarization.
Yeah. Okay. So any comments on any of these topics?
In Manish, but before that, I would like to.
Okay. So Manish. Okay. So Manish, please.
Okay. Yeah, thank you very much. I keep unmuting and it gets muted, so hopefully it stays. So regarding Faraday rotation, I would like to mention that we have a bright future ahead with the square kilometer array. So with the current Pathfinder with POSSUM survey, the Australian square kilometer array Pathfinder, that already observations have been taken, the number of point sources from 1 to 3 sources have been increased to, or is being increased to 25 sources per square degree. And with the full square kilometer array, this can be extended to 1,000 points per square degree ultimately. So the number of sources can be significantly, so like 1,000 times increased, and this will improve the resolution down to the scale of pre-stellar cores. And we're not only limited to point sources, we can also use extended emission for Faraday tomography, actually. And different communities, including myself, have been working on techniques to use Faraday tomography to obtain the line of sight magnetic fields. So instead of using point sources, we use extended emission. And I'd like to also mention that with Zeeman, we also face the same challenges because Zeeman emission can be very challenging, and we usually rely on Zeeman absorption, which again is point sources. So I just wanted to mention these from the quick overview that you gave.
Yeah. Okay. Thank you. Yeah, that sounds great if we can have more and more samples.
Yes. Yeah.
Okay. So any other question or comments?
Yeah, I think I have the thing you discussed about the cross validation between different techniques. Right?
Yes.
So I think from the top, question to Menush and Bao here as well. So you can constrain the angle of 3D magnetic field.
Yeah.
Could you try to do the same thing toward the sideline where we have the Zeeman measurement, and you calculate the line of sight magnetic field, and you compare your derived strength along a line of sight with the Zeeman in the same location to see how well the technique can reconstruct the Zeeman?
Yeah, I think it's possible, but the first thing is we need to make sure we are tracing the same area, because for Zeeman we only use certain chemical tracer, and that might not always align with the dust we are doing the dust continuum.
Yeah, that is a very important point, to make sure that different tracers are probing the same region. So one way to test that is to play with synthetic observation.
Yeah.
So with our Polaris code now, we can accurately predict the dust polarization, and we also can predict the Zeeman polarization. So we can analyze the synthetic data to see whether two different tracers are probing the same region.
So do you also include chemical structure in your model?
Chemical, no, in the Polaris codes, we don't have a chemical reaction, but we have some molecular lines.
Okay.
Yeah, so like a CN line, some very popular lines.
Yeah.
maybe I also add more point because that the Polaris not only just generates about the Z-man measurement for different vocali, but also but syndrome measurement and also for the Faraday rotation as well doing in the Polaris. So now we can compare that for different tracer to see like how we can trace the same region using different tracer compared with the dust polarization. And then from that we can recover the 3D multi-view structure as well.
Okay, that's great. Manoj, did you raise your hand?
Yes, yeah, I did. Thank you. Yeah, thank you, Trump, for your question too. And I strongly agree that it's important to properly test all these techniques that we're developing to identify where their limitations are and make sure that we are probing the same regions. For Faraday rotation technique, we have been getting similar results as Zeeman observation. So for molecular regions, we are getting exactly within the uncertainty range the same direction, and in terms of the strength, the same strength. When we go to the outskirts of the clouds, we are getting exactly the same directions. In terms of the strength, we are getting slightly higher magnetic field compared to Zeeman, but it's interesting that we are getting the same correlations. For example, in Orion A, one side, on average, the magnetic field is half of the other side. And this is seen in atomic Zeeman observations, and we are seeing this in our Faraday rotation observation. So even though in the atomic regions we are overestimating slightly compared to Zeeman, we are getting the same correlations overall in terms of the strength and exactly the same direction too.
Okay, so I'm wondering how do you compare the Zeeman from the Faraday rotation, because Zeeman just observing with a relatively low resolution, but you are using a point source, then you should be concentrate at only one position. So how did you do the comparison?
Yeah, so for molecular regions, we had Zeeman measurements that were very nearby. So the angular separation was minimal compared to the points, and we looked at the magnetic field and they were the same. For atomic regions that we didn't have exactly the same points, I averaged over a large area. So that's how I compared in the outskirts of the clouds. But within the molecular clouds, we had points that were very nearby, and even though and it might have been actually, yeah, I think it was absorption, Zeeman in absorption observations, not in emission. So it was kind of like one-to-one comparison. Yeah.
Okay, thanks. Please.
Okay, so I think I have more discussion about that because that all of us will try to use for different tracer to get the information about the 3D magnetic field, as also we showed that with many technique. But we also feel like, okay, so in order to see like what is the origin of the 3D magnetic field, we also need for different gas kinematic in order to confirm like what is the causing of that 3D structure. Is it causing by the shock compression? Is it also causing by the twisted magnetic field due to the step gravity? So I think the gas kinematic information is also need to combine with the 3D magnetic field that we can get from our technique to get fully understand how they impact into the star forming processes.
Yes, I think right. The velocity information is very important. So but there could be an independent measure because we don't want to, because this is something what we want to test. So we cannot really use include this information in the model, or otherwise we will just in the loop. So I think it's important to have additional velocity information to further analysis. Okay, and
So again, I think thanks, Menush. I might have another question to you, or maybe I'm curious because I really like your method. So in order to estimate the volume density of electron, you use the chemical model. And how do you think about using the light tracer to constrain the cosmic ray ionization rate and radio row here? So I think, do you think it's better than chemical model?
Yeah, that's an excellent question, actually. And if I may answer your previous comment, I think first, so I think the 3D magnetic field geometry itself is telling us where the origin is. So when we look at the geometry, sometimes we see that it's shaped by bubbles, so the origin is by bubbles, and sometimes we see it's shaped by gravity. So I think the answer is 3D magnetic fields. And now about the electron volume density. That's something we should explore actually, because so in the chemical code, what we see is that the cosmic ray ionization has the most impact in providing free electrons inside the molecular clouds. When we turn the cosmic ionization off, we see that we don't have enough electrons to induce the rotation measure that we observe actually. So cosmic rays are very important in providing free electrons, and yeah, maybe that's an approach that we can explore to compare with the chemical results too.
Yeah, I just comment because recently I just visited a group in Paris Observatory with the Matt Yvonne and her postdoc. So they use, I don't know, they use IRAM or NOEMA to molecularize, and they can control the map of volume density, electron volume density. And I think this technique can be very good for you, right? I think to test whether or not it's better or not compared to the chemical model.
Yeah, that's excellent. Yeah, we should definitely explore. And thank you so much for your interest in this technique too. Yeah, let's explore this.
Yeah, I will send you the name of probably the information so we can discuss a little bit later on that. But I think it's very, very important technique here.
Sounds great. Thank you.
Okay, then any more comments?
Okay, so I have one more things to discuss. So here we are discussing about how to derive a 3D magnetic fields.
Yep.
But how about the real 3D structures of filaments or molecular clouds? Because what we are discussing is filaments lie in the planetary sky.
Right.
But how about they are, in reality, they may be inclined with respect to the planetary sky. So how would we probe such a 3D structures in the real?
So it's quite difficult. I think one possibility is that if you can directly measure the volume density using like multiple molecular line transition, then if we know the volume density, we know the current, we can directly measure the current density from a map. Then we know the thickness at each pixel, and by comparing the line of sight thickness and the width we measure on pencil of sky, we can really know the inclination angle of the filament. That's possible, but that's very complicated. So we need more.
Yeah, that is very especially important for the evolution of a half filament system.
Yeah, yes.
Because we cannot expect that all filaments are in the same plan and then
Right.
make the hub. That is
right, but the multi-transition observation takes time, so it's, I think up to now, not many people is working on that. So it's, yeah, it's important.
The Astro 2020 decadal survey.
Yeah.
One of the pressing issue raised in the survey is 3D structures,
right.
Not only magnetic fields but density structure as well.
Okay, then any point that anyone want to discuss? Okay, so if that's all, then maybe we can close this session for lunch. Okay, so thanks. So LOC, you want to announce anything? No, so we just go to lunch.
Sorry, so no announcement from the LOC. So I think we can take some 5 minutes break and then lunch. And the next section in this afternoon will start at 1:30. Yeah. Cái này ý em là